Okay, welcome to part 6 of the video series, Fundamentals of Reinforcement Learning. And in this part, we are going to basically implement Q-learning algorithm in NumPy. In the previous part, we discussed SARSA algorithm in detail, and we saw how Q-learning is different from SARSA. And in this particular video, we actually are going to code Q-learning algorithm on a map rover example that we have seen in the earlier parts of this video series. So just as a recap, consider, for example, a map rover agent that has to walk through in this grid world where you have state 0, you have state 1, state 2, 3, 4, 5, 6, 7, 8. These are the states of the grid. And if you are in state 0, then you have reward 0. All the states have reward 0 except state 4, which has reward -1, and state 8, which has reward 1. Further, let's assume that state 8 is a terminal state, which means once you reach at state 8, the game just finishes, or the map rover just wins, or the episode just terminates. Otherwise, the map rover has to take certain steps. For example, if the map rover is in state 0, then in the next time step, the map rover can take an action, go right and move to state 1, or maybe go down and move to state 3, or stay there. That's an action. And in the next time step, the map rover may stay at 0. Obviously, if the map rover is in state 4, then there are actions: go right, that will lead to 5, go left, that will lead to 3, go up, that will lead to 1, go down, that will lead to 7, and stay there, that will lead to 4. So these are different actions, and this is the initial Q matrix. The one way of implementing this state action pair in this particular case is just to implement the state and state pair. So for example, 0 to 1, so transition from 0 to 1 will happen only with a unique action. So rather than so that's one way of implementing that. You rather than writing actions there, you write states there, and the state and state pair actually give rise to a unique action, which corresponds to a state action implementation. So that's one way. There are other smart ways as well. So we initialize all our Q matrix with 0, and wherever we cannot reach, we initialize those by nan. And let's now implement our Q-learning algorithm for this map rover example, which is the following. We initialize, we randomly sample some state, and then we follow all the Q-learning algorithm that we saw earlier in our previous video. So yeah, so let's go to Jupyter Notebook and implement this. So first of all, we need to import some packages. In this case, we need to import NumPy as np, so we import that. Next, what we do is we set our matrix empty, and let's say this is 9 by 9. We have 9 states. If you remember, we have 9 states starting from 0 to 8. We have 9 states. So let's say we have this as empty. So we initialize all of these to be nan, np.nan, and which means all of these entries are nan. Now we fill these zeros wherever the actions lead to the states. For example, from 0 to 2, there is no action that leads from 0 to 2, and we will keep the value nan here and all other values. So we initialize everything with nan, and now with respect to these transitions and actions, we fill these zeros progressively for each. So let's do that. So Q from state 0, we can go to 0, 1, and 3. As you can see, from 0 we can go to 0, we can go to 1, and we can go to 3, and we initialize that with 0. Next, from state Q, state 1, we can move to where we can move from state 1. From state 1 we can go to 0, we can stay at 1, we can go to 2, and we can go to 4. So 0, 1, 2, 4. So 0, 1, 2, 4, and we initialize that with 0. Yeah. So from state 2, similarly, we can go to 1, 2, and 5. 1, 2, and 5, as you can see from the slide. From state 3, we can go to 0, 3, and 4. 0, 3, and 4, and we initialize that with 0. From state 4, we can go to 1, 3, 4, 5, 7. From state 4, we have a lot of actions. We can go to 1, we can go to 3, we can stay at 4, we can go to 5, and we can go to 7. So for 4, we can go to 1, 3, 4, 5, and 7. 1, 3, 4, 5, and 7. Yeah. So that is 0. Now from state 5, we can move to 2, 4, 5, 8. So 2, 4, 5, 8, just setting up the initialization. From state 6, we can the map rover can move to 3, 6, and 7. So 3, 6, and 7, that is 0. From state 7, the map rover can move to 4, 6, 7, 8. So 4, 6, 7, and 8, that is 0. And from state 8, the map rover can move to 5, 7, and 8. 5, 7, and 8, according to the slide we just saw. So after that, our Q matrix looks like the following. It has a lot of NaN entries, but there are the 0 entries exactly in the places right here. So that's our Q matrix initialized. So once the Q matrix is initialized, basically we are here. We have done this step 1. Now what we do is we must have the reward matrix for us, because we must have the immediate reward matrix. And as we can see here, the reward for reaching at state 4 is always -1. Reward for reaching at state 8 is always 1. And reward for everywhere else reaching at every other state is 0. So we can build a reward matrix R just like Q. But then what we do is we say, okay, IDX where np.isNaN R, the fourth column. So wherever there is NaN value, what are the indices where there are NaN values? NaNs. So R, other than these indices, complement of that, in the fourth column, place a -1 there, because whenever you end at state 4, you reach at state 4, you, with whatever action, you receive a reward of -1. Next, we do the same trick for the state 8, np.isNaN R 8, that's the index, and R complement of this index at the column 8 is 1. So all set, I guess. So now we see our reward matrix. It is exactly like the Q matrix, but in the fourth column, wherever reachable, you have -1, and in the eighth column, wherever reachable, you have this 1. Now, once we have this R matrix with us, with this Q matrix with us, the initialization, we have done initialization. Now we basically move to our Q learning algorithm with that starts with the random sampling of a state and all the steps that follow from it. But for that, we need to set the maximum number of episodes. But because whenever the terminal state reaches, we have explored 1 episode. So this algorithm runs for a number of episodes. So let us just set some parameters. The max episode, max number of episodes. So let's define that as max episodes. let's say our maximum number of episodes, let's set them to 100. Now we also have to set the number of states, which are 9. So let's keep the number of state as 9, or maybe we have num states equals to 9 in this particular case. We also have to set a gamma. Remember, this gamma is this discount factor. So let's set the gamma for this particular problem. Let's set the gamma for 0.9. I'm not saying 0.9 is the best value for this. I'm just setting this up. And also let's specify the terminal state to be the state 8. That's our terminal state. So now we have our most of the parameters set. We can set this alpha here, maybe a constant value, or maybe we decrease the alpha as we move on. So let's set this alpha in each episode. As we move in episodes, the alpha will decrease progressively. So we can set the alpha inside the loop. So we have these values defined already. So now let's move to our loop. For k in range max episodes, that's our episode loop. What we do is we set the alpha value. Alpha is 1 over, let's say, k plus 1, where I'm adding this 1 just to avoid this 1 over 0 case in the very first episode. That's our alpha. Then now let's sample some state randomly. Let's just sample some states. So let's say I is our starting state. Np dot random dot permutation and np dot range num states. So this will permute all these 0 to 8 numbers, and let's pick one of them randomly. So that's the random sampling of one state. That's one way of random sampling the state. So we now set our initial state randomly. Now we will sample an action, maybe by an epsilon greedy choice. We will sample an action for this state. So let's sample an action. But before sampling an action, we have to deploy a loop, because we will quit that loop whenever the terminal state reaches. So select max. Are we going to select the greedy? Are we going to select the greedy choice or the other? So for example, in the beginning it is false, and then what we do, if np dot random dot rand, if that is smaller than some value, let's say this is the probability of selecting the let's say 0.5 is the probability of selecting the greedy choice, and 0.5 is the probability of selecting any choice at random. And this probability can be set to different values. I'm using just here 0.5. Then we say, okay, select max is true, otherwise it is false. So now what we do is idx is equal to np dot is nan, where we have this these nan values. So these are all the indices that are not reachable from I. So let's find out the allowed states that we can reach from I. So allowed states is basically np dot range num states, and from these we have to pick the states that are reachable. So this is index of non-reachable states, so we pick the indices of the states that are reachable. So these are the allowed states from I, the state I. Next, what we do is we just pick j as the maximum from I to allowed states dot arg max. We pick the argument that is maximum. That's a greedy choice. If we do the greedy choice, then so j is the index of the maximum. So if we have this select max, if that is true, then j basically is allowed states j. This is the state that is the next state by the greedy choice. Else j can be picked just randomly. So np dot random dot permutation, and we have allowed states, and we just permute them and pick one randomly. So that's so if we do the greedy choice, then our state is the max state. Otherwise we just pick any state from all of the states. By the way, technically when you do not pick the greedy state, then you should pick the state randomly from the rest of the state, avoiding the greedy choice. But this works as well. I mean, this works also fine if you just include the choice of greedy state in the uniform random distribution as well. So that's perfectly okay. It has an impact of just increasing the probability of selecting the greedy choice. That's all. So now we have our next state, which is st plus 1. That's our next state. Now what we do is we update our q. So q ij, the previous q is basically q ij plus alpha asterisk. This is our estimate. Return ij, remember this equation, this return, and then we have this plus gamma asterisk q. Oh, by the way, here we have to pick this q to be the maximum. From st plus 1, from this particular state, we have to pick the q that is the maximum. So we have to pick this q by the following: np dot nan max q j nat. So that's our q, and then we have to subtract it from it. We have to subtract this q ij. So that's perfectly the update that is there in the q learning. So see here, we pick the action or the next state completely greedily. So yeah, so that's our q. Next what we do is after updating the q, we basically check if I is terminal state. If that's the case, then just break, and if whether or not, then assign the next state to be I. The next I is st plus 1, which is j. So that's the q learning training, or the learning process. That's the code for it. Let's just run it. If there is no error, it should run properly. So let's just run this cell. Yeah, it runs properly. So now let's see the q matrix after learning. The q matrix looks like the following. It has these kind of values. Obviously the nans, they stay nans, and the rest of the values, they are like these. Now we have our q value. Now let's see the policy. Let's learn the policy. Let's say we start from particular state. Let's say I is equal to 0. We start from this state and we do num transitions. Let's say we do the 10 transitions from there. So what are the states that we should be visiting when we start from state I? So for k in range num trans, for k in range num transitions, what we do is we print that we have visited this state. Then what we do is we select the indices np dot is nan Q. So we select the indices that are not reachable, and then we will pick the allowed states as a complement. NP dot range, the total number of states are 9, and we pick the states that are reachable. These are the allowed states, and J is simply the max states. So Q from I to allowed states, allowed state dot argmax. That's the index inside the allowed states. So we pick the particular state. Let's say J is allowed states J. So the next state basically is J. So we set that I equals J, and in the next transition that J will be printed, and so on. So let's see, if we start from 0, what kind of states the map rover will visit after its learning. So yeah, if we start from 0, it will go to 3, then 4, then 7. That's awkward. It should not visit 4. Why is it visiting 4? It should not visit 4. Maybe we have to set certain parameters differently, or maybe we because the 4 is -1, so starting from 0, it should never visit this 4. Maybe we have to set the certain parameters differently. For example, the learning rate, or gamma, or alpha, maybe, and that will give us a different result. For example, let's say our gamma is let's say 5. Let's say just the gamma is 5, and see what happens. So now we run that, and we have this 0, 1, 2, 5, so it is avoiding. So all am I telling you that these hyperparameters, they have huge impact of in your learning. So setting up these discount factors and these learning rates, they have impact on your learning. So what if we start from, let's say, what if we start from 2? What if we start from 2? So we end up from 2, we go to 5, and then 8, and then we'll stay at 8. So the map rover learns that. What if we start from, let's say, 6? If we start from 6, it go to 7, then 8, and then it stays at 8. So it learns a very good transition. So from whatever, after learning, whatever state you start the map rover from, it learns to reach to 8 to maximize its reward using this Q learning. So that's the implementation of Q learning. Very basic kind of implementation with very, very basic kind of settings. Obviously, these are not the best values. The gamma or alpha maybe, or maybe the probability of epsilon greedy probability values. Maybe these values has to be set more carefully, but that's the basic essence of this Q learning, and we run that Q learning on this map rover. In our full course on AI sciences related to reinforcement learning, we actually go much deeper into these algorithms and these examples to the level of non-tabular methods, where we approximate these Q functions using parametric functions and deep neural networks. And there is a lot of fun stuff and much more detail of reinforcement learning in our full course on AI sciences. So if you want details of reinforcement learning in a much practical sense with Python coding, all that stuff, so I would recommend to enroll our course on AI sciences. That is the reinforcement learning course, and that will give you a very deep understanding and a very practical understanding of the subject. So if you have liked our content, please like us, share to your friends, subscribe our channel, and hope to see you next time.